Thank you for inviting me to give this seminar. Today's topic is active fault management for enhancing microgrid resilience. I'm Peng Zhang from Stony Brook University. I'm leading Stony Brook's power engineering program. My research topics include AI-enabled resilient power grids, microgrids, and network microgrids. Also, we're focused on grid resilience and a few other topics. Today, we will discuss active fault management in microgrids. 5 topics will be covered. First, we'll discuss why active fault management is important and difficult. Second, we'll introduce AFM formulation and a centralized solution for a limited number of microgrids. Third, we'll introduce distributed and asynchronous AFM, which allows online AFM solutions for regulating the performance of multiple microgrids. Then, we will discuss how artificial intelligence can make AFM more scalable so that it can manage hundreds of microgrids and distributed energy resources in real time. Finally, we will discuss the future work in this area. Why is active fault management important? First, let's briefly introduce microgrids. The microgrids are a promising new paradigm for electricity resilience. A microgrid is an autonomous local power grid formed by a collection of power loads, distributed energy resources, or DERs, and coordinated control. It can flexibly host renewables and energy storages, and operates continuously even without the utility supply. Further, if multiple microgrids are interconnected and well controlled, those network microgrids will offer much more resilience benefits and can even help utilities to quickly restore power supplies. Although high level of microgrid penetration has significant resilience benefits, it creates a difficult dilemma. Let me explain. Today's microgrids are very sensitive to grid faults. When fault happens, they normally will trip themselves offline and operate in the islanded modes. As a result, when many microgrids are interconnected, a minor fault or grid disturbance may induce a sudden loss of a large number of microgrids, which would significantly increase the risk of blackout in both distribution and even transmission grids. This risk is real, as there are multiple events happened in the past few years. One example is the loss of nearly 2 gigawatts of solar PV systems in California in August 2016, triggered by a remote grid fault. Another event is the Odessa disturbance happens June 1st, 2021, where 2.6 gigawatts of PV and synchronous generators were lost, triggered by some remote grid faults. Another one is a London blackout on August 9th, 2019. In that event, 1.9 gigawatts of wind and gas turbines were lost, triggered by, again, some remote grid faults. For this reason, the IEEE has published a few new standards, and Federal Energy Regulatory Commission also issued new policies, which encourage or require microgrids to have fault rescue capability so that they can continue injecting power when the main grid is disturbed by faults. On the other hand, if we require microgrid to stay online with a grid fault, what would happen? So if network microgrids intend to rescue faults, uncontrolled power and fault currents will be injected into the main grid, which will violate the fault current limit of the grid, causing equipment damages, overvoltages, instability, and power quality problems. So meanwhile, disturbances in the utility grid would propagate into network microgrids through synchronized electrical links and plague microgrid end users. To address this difficult problem, we developed a new concept called active fault management, AFM. The new approach allows network microgrids riding through balanced and unbalanced grid disturbances, systematically enhancing grid resilience rather than negatively impacting the disturbed power grid. With AFM, microgrids can serve as reliable resilience resources for both local customers and the Microgrids. When a fault happens, instead of changing into island mode, the AFM enables a microgrid to stay online and achieve the following objectives. First, maintain the magnitude of total fault current unchanged. How can we achieve this? We will shift the phase angle of the microgrid fault injection through inverter controls. Second, eliminate the damaging power ripples caused by grid faults. How to achieve this? We can properly set the angle displacements between three-phase microgrid currents. Then, the double line frequency power ripples can be cancelled out. Third, power flow of microgrid should be roughly identical before and after fault in order to maintain microgrid stability. How to achieve this? So we can achieve this by altering the three-phase current magnitudes of the microgrid. Since AFM was proposed around 2015, it started with a centralized version, applied on a single microgrid. Later, we moved to a distributed AFM for network microgrids, and eventually a very efficient distributed asynchronous algorithm has been developed. AFM's application has also been extended to control various types of renewable energy resources, and they have been widely tested on the hardware-in-the-loop testbed. Most recently, we developed a learning-based AFM, which can perform fault measurement in a few milliseconds, and can handle dozens of even hundreds of microgrids and DERs in real time. It is also being implemented in IoT and edge computing devices to reduce its cost. So we start from a centralized AFM designed for regulating fault current contributions from a single microgrid. When the fault happens close to a microgrid, the main grid contributes fault currents to the fault location. So does the microgrid. The total fault current is the sum of the two components. Meanwhile, power ripples will be induced in the microgrids after fault happens. We now formulate active fault measurement as an optimization problem. There are two components in the objective function. One is microgrid's fault current contributions, meaning the difference between the total fault current and the fault currents from the main grid. The second component is the magnitude of double line frequency ripples in the microgrid's power flows. We add three constraints in the optimization problem. Constraint number one is power balance. Constraint set number two is used to guarantee that the sum of inverter's three-phase currents is zero. The purpose is to make AFM applicable to any power grids with or without grounding. Constraint set 3 is used to ensure that there are no overcurrents in the microgrids. Now let's look at some experiments. In this experiment, we are showing the effectiveness of AFM. Here, a single phase-to-ground fault is applied close to a microgrid at 0.4 seconds and is cleared at 0.7 seconds. As we can see, even though microgrid fault current is quite large, AFM is able to keep the total fault current unchanged, meaning the net fault current contribution is kept at 0%. Without AFM, we can see an increase in the total current by 25%. So with AFM, the double frequency power ripple is limited to 7% or so. Without AFM, however, the power ripple is 9.01% of the average power delivered. To manage network microgrids, we need AFM that can deal with plug-and-play of microgrids or microgrid components. AFM needs to be computationally more efficient and should be able to preserve privacy among microgrids. To meet all these needs, we propose a distributed and asynchronous AFM, DAAFM. The salient features of DAAFM include, first, we adopt a distributed optimization formulation that supports online plug-and-play of microgrids. Any AFM objectives can be added into or removed from the formulation easily. Second, a very efficient solution, distributed and asynchronous surrogate Lagrangian relaxation, DASLR method, is employed to coordinate various microgrids during faults. It is particularly powerful in dealing with mixed integer programming problem in real microgrids, where we have both continuous variables and discrete variables. Third, we use a software-defined networking architecture to ensure low latency in DAAFM, making DAAFM fast and programmable and resilient to communication failures, data losses, and cyber attacks. If we compare the centralized AFM with DAAFM, the main difference is that the system-wide safety constraint that couples all the microgrids will be relaxed into the objective function by using Lagrangian multipliers lambda. The resulted relaxed model is decomposed into n subproblems. Each subproblem actually is the AFM for an individual microgrid. Subproblem solutions are then coordinated by a coordinator, which may reside in the distribution grid operation center to update Lagrangian multipliers and achieve the global optimal solution. The coordinator updates lambda immediately after it receives the AFM solution from one microgrid, without waiting for other microgrid to finish their AFM calculations. This makes DAFM asynchronous. Also, DAFM supports smooth and convenient plug and play. After the connection or disconnection of certain microgrids, no change is required for each microgrid algorithm. The only slight change is a computation of lambda performed by the coordinator. The figure on the right-hand side shows the optimization calculation sequence along this process, and which shows that the DAFM is very efficient. We performed case study for DAFM on a 6 microgrid system, and we studied many different cases, including single line-to-ground fault, double line-to-ground fault, face-to-face fault, three-phase fault, and many other scenarios. Any of these tests, DAFM performs really well, and it achieved the objectives we set up. Now let's look at this video that illustrates how AFM protects network microgrids after fault. This is a testbed, real-time testbed. Network microgrids are formulated in the real-time simulator, RTDS. And AFM is located in the remote server. So this shows that when the fault happens in the system, we first look at the system performance without AFM. As you can see, after fault happens, the total fault current significantly increased by almost 20%. Now, let us activate AFM in the system. And with AFM activated, once a fault happens, AFM will quickly bring down the total fault current contribution. Now, let's see what happened to the system after three-phase fault happens with AFM activated. After AFM is activated, the incremental fault current from network microgrids is effectively kept at 0%. AFM is found not only being able to improve resilience of network microgrids, but also can increase hosting capacity of renewables. We use one example to show this benefit. In this test system, we have one wind farm connected close to 2 PV farms. And we set up a testing environment using RTDS and connected with the 3 renewable energy plants. The 2 PV farms are equipped with AFM, and a wind farm does not equip AFM. Now let's look at the test results. When the AFM in the PV systems activated, as you can see, when the system fault happens, the wind farm was able to ride through the fault without activating its crowbar protection, which is very good, which means that the AFM equipped in the PV system not only help the ride through of the PV system themselves, but also help the neighboring wind farm to ride through faults. Now, let's look at what happens if the PV system only equipped with a simple ride-through method. So the result is on the right-hand side. As you can see, even though the PV system themselves ride through the faults, the wind farm failed to register the faults with the crowbar activated. And as a result, the wind farm was offline during the system fault. Next, let us quantify the resilience benefits of using AFM by calculating the resilience indexes. The indexes we are using here was introduced by Dr. Bill Anderson from ONR. And in the resilience index, we have invulnerability. That shows how the system is robust to disturbances. The recovery index is used to quantify how fast the system will recover from disturbance. And resilience here is defined as a weighted sum of invulnerability and recovery indexes. So now we did the calculation using the resilience metrics on the AFM performance. As you can see, if we look at the voltage magnitudes of the PV farms, the resilience improvement is visible. And even better, so if we look at for the current contributions of DERs, when we calculate the resilience indexes, as you can see, the AFM is able to significantly improve the resilience of the system. So for example, the invulnerability has been improved from 5% up to 100%. The recovery is also improved from about 15% to 67.5%. And the overall resilience also have a significant improvement. We did a lot of experiments, and we can find that the distributed synchronous AFM can meet real-time fault management requirements for a system with dozens of microgrids. By testing the performance of DAAFM, we found that DAAFM can generate reference values fast enough for a system with several microgrids. But more microgrids lead to more computational time. In general, distributed optimization-based AFM would fail to meet real-time requirements for a system with dozens of microgrids. Because of this, we developed a novel federated learning-based AFM. So in our field tests, learning-based AFM can always generate reference values within 10 milliseconds, regardless how many microgrids it manages. In the federated learning-based AFM, each microgrid will train its own AFM locally. And then there's a neural network to coordinate the local optimization process into a global optimization solution. Federated learning keeps data and the training localized, preserving privacy and leveraging local computation and data storage resources. We did some study on a 6 microgrid system to test the performance of the learning-based AFM. As we can see, learning-based AFM is able to regulate the fault current in the systems and improve the voltage profile in the main grid as well. The most important improvements is the reduction of computational time. Learning-based AFM can be finished within 3 milliseconds. That also includes 1.8 milliseconds of two-way communication time. Meanwhile, optimization-based AFM has significant delays for large-scale systems with many microgrids. For example, for the system with these 6 microgrids, it takes about 54 milliseconds to generate the control signals. This will compromise its performance. We also tested learning-based AFM on a much larger system with 36 microgrids. And the computational time does not increase while the number of microgrids increases. We expect AFM will be widely used in the power grids. So with the penetration of AFM in the power grids, naturally the question is whether AFM is safe, meaning whether AFM impede the grid control and protection relay operations or not. We did some field tests, and we can show that AFM is always safe. We built a large MPCC system to test the performance of AFM. First, we disable AFM in the system, and we observe the distance relay performance when the system has a fault. Next, we activate AFM. After that, we can see that with AFM heavily penetrated in the MPCC system, the distance relays in the system always perform exactly the same as before, meaning AFM does not affect the relay operations. So we have demonstrated the correctness and the efficiency of AFM for microgrids, network microgrids, and large-scale power systems. In the future, we believe that there are several new directions we can pursue. The first one is a sequence AFM. So we plan to use AFM to regulate the symmetrical components of the currents injected into the power grids. The second direction is that we want to demonstrate the scalable deployment of AFM. So we want to deploy the IoT-based AFM devices in a power system penetrated with hundreds or thousands of DERs. The third one is a cybersecurity in AFM. So we want to deploy a few layers of protection to make sure that AFM is resilient to different types of cyber attacks in the system. Yeah, that's all of this presentation. Thank you very much.